Welcome to physics class on Oersted experiment and Biot-Savart's law, its applications on circular coil of CBSE class 12, chapter 4, moving charges and magnetism. Before 1820, electricity and magnetism were studied and thought of separate entity or branches of physics. During the lecture demonstration in 1819, Danish scientist Hans Oersted, a physicist and chemist, professor at Copenhagen, found that an electric current in a wire can deflect a nearby compass needle. He observed the relation between the electricity and magnetism in 1820. He performed a simple experiment which established the relationship between electricity and magnetism. After this momentous discovery, linking a magnetic field and an electric current for the first time was the beginning of our understanding of the origin of the magnet. And after this momentous discovery, the interrelation between this magnetism and electricity, these are inseparable. It is just like the two faces of a coin. Oersted's experiment. When a large current was allowed to flow through a wire AB parallel to the axis of a magnetic needle kept below and sufficiently close to the wire, the needle was found to deflect from its normal position to the position as shown in figure 1a. That means when the current is allowed to pass through this conductor AB and the magnetic needle which is kept below this current carrying conductor, when current is passed through this conductor AV of sufficiently large amount, and if this magnetic needle is placed below the current carrying conductor and close to the conductor, then what happens? As soon as the current is allowed to pass, then the magnetic needle of its north pole is deflected as shown in the diagram like this. Next, the deflection of the needle. The deflection of the needle is found to be in the opposite direction on reversing the direction of the current by reversing the polarity of the cell as shown in this second figure. The deflection of the magnetic needle changes with the strength of the electric current. That means when you increase the amount of current flowing through this conductor, then the amount of deflection is also more. It increases, that means the deflection increases with the increase of the amount of current flowing through the conductor. These observations led Oersted to interpret that there must be some magnetic effect around the wire carrying electric current which deflected the magnetic needle. He concluded that an electric current, that is flow of electric charge, produces magnetic effect in the space around the conductor. In other words, flow of electric charges is the source of magnetic field around the conductor. Now you can also see like this, if a current is passing through a point here like this, and if the direction of the current through the conductor is outward, then if you place a magnetic needle around it like this, then the magnetic needle of whose north pole will be pointing in this direction. So that means if a current carrying conductor of whose current is coming outward is drawn by this dot line like this, and then what happened, the magnetic field direction will be in this direction, anti-clockwise. Got it? And suppose if the current carrying conductor is placed perpendicular to this plane and the direction of the current is getting inward inside, then what happened, the direction of the magnetic field that will be given by the direction of the north pole here. The red represents north pole of the compass needle, so the direction of the magnetic field will be in this direction like this. Got it? So the current carrying conductor, if it is there, then around it magnetic field is always there. So current carrying conductor, we say simply current carrying conductor always associate magnetic field around it. Mind you, again, the magnitude of the strength of the magnetic field, that will depend upon the amount of the current flowing through the conductor. More the amount of conductor, more will be the strength of the magnetic field. Now let's see how to find out the direction of the magnetic field, and it is known as what Amperes swimming rule. It states that if we imagine a man swimming along the wire in the direction of a current with his face turned toward the needle, so that the current enters through his feet and leaps at his head, then the north pole of the magnetic needle placed below the wire will be deflected toward his left hand. So what does it state? It states that if we imagine a man swimming along the wire in the direction of a current with its face facing turned toward the needle, so that the current enters through his feet and leaps at his head, then the north pole of the magnetic needle placed below the wire will be deflected toward his left hand. So let's see the figure again, the previous figure, and I will explain you this again. And there is another similar rule, just to know it, this a simpler one, which is known as SNOW rule. That means snow rule, we simply say. So let's see the previous the diagram again, and I will try to explain you about this Amperes swimming rule. Suppose if you take it that there is a man swimming here, okay, a man swimming here like this above the current carrying conductor, okay, with its face turning toward the current carrying conductor. Let's take it that this is a nose, so that the man is allowed to swim above this current carrying conductor in such a way that the current flows from his feet and toward the head. It moves in this direction. Then the direction of the deflection of the north pole of the compass needle placed just below this current carrying conductor will be in the direction of his left hand. That means left hand, this is right side and this is the left hand. So the north pole of the magnetic needle placed below this conductor will be toward the left hand. Got it? Understood? Yes, in that way. Got it? So let's try to see the simpler one, which is known as what? Snow rule. The snow rule is an abbreviation SNOW: south, north, over, and toward west. This represents south, north, over, and then W represents west. What does it mean? It means if a current flows through the from south to north in a wire held over the magnetic needle, the north pole of the needle will be deflected toward the west. Got it? Suppose in that previous diagram, again, let's go to that previous diagram, this one. Suppose it means that if a current flows from south to north of a compass needle, that means current is flowing here, the current carrying conductor should place above or over the compass needle. Got it? Over the compass needle. That O represents over. So it means if a current flows from south to north of a compass needle in a wire which held, okay, over the magnetic needle, then the north pole of the needle will be deflected toward the west. This is south, north, west, east, okay. So this north pole will be deflected toward the west. I'm repeating again the statement. It means if current flows from south to north of a compass needle, okay, of a compass needle, that means the current conductor, the current is not flowing onto this compass needle. Got it? It is placed above this compass needle, and if that current flows from south to north direction in a wire held over the magnetic needle, then the north pole of the needle will be deflected toward the west. So this is somewhat similar. There is also another easier one also, and the most easiest one, I should say. We can take it that as right hand curl rule. That right hand curl rule, it will come later on, I will tell you, okay. Yes, so let's go quickly the statement of these two rules. If you want to note down, then you can pause this video and you can note it down, okay. So let's go to that next type, how we can do the experiment about this. So let's see. This is a cardboard, okay. This is a cardboard, and you puncture it, this cardboard, somewhere here. You make a hole, and through this hole you allow to pass a conductor, and the two ends of the conductor is made to connect to the two poles of a battery. Got it? This red sign represents plus, this blue sign represents what? Negative. Okay, this is positive and this is negative. If it is allowed to connect, then current will pass through like this, in this direction. Got it? And if you make it this as a center and draw a circle like this, got it, over this cardboard, and if you place four compass needles, small four compass needle like this, just opposite to each other like this, on to the circle, then what happen? As soon as the current is allowed to pass, then what happen? This compass needle of each north pole will be directed along this, in this direction. What happen? When there is no current in the wire, all needles will point in the same direction. Because of what? Because of the presence of Earth's magnetic field at that place. Got it? All the magnetic compass needles will align in the same direction before current is passed. But when current is allowed to pass, then what happen? The compass needle will try to orient along this tangent of the circumference like this, in this direction. Got it? When the wire carries a strong current and steady current, I should say, okay, because this is a DC current, or rather we call it them as steady current. That means the magnitude of the current changes, okay, doesn't changes with time, okay. So what happens when that wire carries a strong steady current, however the needles all deflect in the direction of a tangent to the circle. Got it? As I have said. Got it? So what happened? These can be also done. The direction of the magnetic needle can also be given, or can also be found out by using what I have said as the right hand curl rule, or right hand thumb rule, we can also say. So that is how this right hand rule or right hand thumb rule is here. So what is this right hand thumb rule? Suppose if you try to hold or grip a current carrying conductor passing through a particular point where you want to find the direction of the magnetic field. Suppose if you want to find the direction of the magnetic field at this point somewhere here, then you just try to hold or grip this current carrying conductor by your right hand, okay, such that the direction of the current is along the direction of the current. Then the direction in which your four fingers, okay, the direction in which your four fingers curl that will give you the direction of the magnetic field at that point. Suppose if you want to find the direction of magnetic field at this point, then you need to curl, okay, you need to curl just to hold this current carrying conductor by your right hand, such that the direction of the thumb is in the direction of the current through the conductor. Then the direction in which your four fingers curl will give you the direction of the magnetic field at that particular point. Got it? That is what we call as right hand thumb rule. Now let's see about the Biot-Savart's law. Now this Biot-Savart's law gives you the the magnitude as well as the direction of the magnetic field produced by a small elemental length of the current carrying conductor. Okay, let's see. Now think that this is a current carrying conductor, okay, XY. Let's take it that this XY is a current carrying conductor carrying current I, okay, along this direction like this. And let P be the point of observation where you want to find out the magnetic field. Got it? Due to the elemental length of this current carrying conductor AB of length dl. Now your current I is a scalar quantity, but when you take an elemental current carrying conductor IDL, that means the current is restricted to flow along this direction only inside the conductor. Got it? So that means IDL, okay, we call it as elemental current. That elemental current, okay, onto this conductor is a vector quantity. If you take it that is IDL, then it will be a vector quantity, okay, and where R is the position vector of that point of observation from that elemental length, and theta is nothing but this is the angle between the position vector of the point of observation and the elemental current. Now Biot and Savart found that this magnetic field produced by the elemental current carrying conductor at this P of distance R, then it is found that this magnetic field depends upon various factors. Let's see. It depends upon the amount of the current flowing through the conductor, okay, through the elemental conductor I should say. If the current flowing through the elemental conductor is large, then the magnetic field produced here will be also large. That means if I is large, the small magnetic field produced there due to this elemental length, it will be denoted by dB. That dB will be also large. It depends upon also on the length of this elemental conductor. Got it? dB is directly proportional to dl. That means length of the elemental conductor. Longer the length of the elemental conductor, then what happens, magnetic field induction will be also large. It also depends upon the sign of the angle between this position vector and the elemental conductor, sine theta. Got it? And inversely proportional to the square of the distance between the elemental conductor and the point of observation. So combining these above factors, we get that dB is directly proportional to IDL sine theta by r square. We can write it in that way. Or if you want to change this proportionality into equality, then you require a constant k like this, where dB is equal to k times of IDL sine theta by r square, where k is a constant of proportionality, okay, which depends on the system of units chosen and the nature of the medium between the elemental current IDL and this point of observation. In SI unit, k is equal to what? Mu naught by 4 pi. In CGS unit, k is equal to 1, okay. And let's see, if we place it this current carrying conductor what inside a vacuum, that means in vacuum, okay, there is no medium at all in between IB, IDL and P. So let's see. In SI unit, what happened? I told you that K is equal to mu naught by 4 pi epsilon naught. Why we are taking this in SI unit K equal to mu naught by 4 pi epsilon naught? It depends upon the medium as well as the system of units chosen. So if we make the medium in between the current element and the position vector as vacuum or free space, then what happen? Its SI unit will be equal to mu naught by 4 pi. What is this mu naught? Mu naught is nothing but this is the absolute permeability of free space or vacuum. How much the electric line of force can permeate through that particular medium, we call it that as permeability. Okay, so mu naught is nothing but this is the absolute permeability of free space or vacuum, of whose value is equal to what? 4 pi into 10 to the power minus 7 Tesla per ampere meter. Okay, so try to remember this value whenever you are trying to calculate this in relation to the application of this Biot-Savart's law or anything in the magnetism. Then you will always come this constant mu naught by 4 pi epsilon naught, and this mu naught by 4 pi epsilon naught will be equal to 10 to the power minus 7. Okay, that value you need to take it, right? So like that, what happened? If you want to write it that, then dB is equal to, instead of K you put it that mu naught by 4 pi epsilon naught. Okay, mu naught by 4 pi into I dl sine theta by r square. Okay, this is the magnitude of the magnetic field that is produced by that elemental current carrying conductor of distance small r from it. Okay, and theta is nothing but this is the angle between that position vector r and I dl. Got it? Now you can also write this in a vector form. Why? Because your magnetic field is a vector quantity, so we can write it in the form of vector also. So to write this magnitude in terms of vector, then we need to put one arrow above this magnetic field dB. So dV vector is equal to mu naught by 4 pi I dl vector cross r cap, where r cap is the unit vector along the direction of the position vector r, divided by r square. Now angle between r vector, that means position vector, and I dl, that was sine theta, that was theta, is not it? So if you do this cross product of these two, then you will get it that I dl sine theta will come again. Got it? So instead of this I dl sine theta, you can write as I dl vector cross r cap divided by r square. Or you can also write this instead of r cap, if you want to express it in terms of its vector notation, then what happened? Your r vector, we can write it that r vector is equal to what? Its magnitude, that is equal to r, okay, times its direction, like this, r cap. Got it? So your r cap will be equal to what? R vector divided by, if you transfer this r to this side, then it will be equal to r, like this. So if you want to express this r cap in terms of r vector here, then what happened? One r comes in the denominator, so that r and this r square will give you r cube. So in the form of what, that vector notation, you can write like this. Got it? dV vector is equal to what? Mu naught I dl vector cross r vector divided by r cube. Mu naught by 4 pi will be always there. Mu naught by 4 pi times I dl cross r vector divided by r cube. So this will give you the direction of the magnetic field. So the direction of the magnetic field being a cross product is there, so we can give the direction of the magnetic field in the direction given by the cross product of these two vector I dl and r vector. Okay, or you can simply use that right-handed screw rule or right hand rule that we have just done just now, that one. Or instead of that also, if you try to use that right hand curl rule also from the first vector, if you try to curl your four fingers stretching mutually perpendicular to the thumb, and if you try to curl from the first vector to the second vector, then the direction of the thumb will give you the direction of this dv vector. Okay, and this dv vector will be perpendicular to both idl and r vector. Or you can also say that the dv vector will be in the direction in a direction perpendicular to both this vector. Okay, or you can also say that this dv vector will be in the direction, okay, perpendicular to the plane containing both this idl and r vector. This you have learned in your class 11 at the time of the cross product of vectors. Okay, yes. Now if you want to express this magnetic field induction, that means dv, due to the entire wire, then you need to integrate it this. Okay, you need to integrate it, then you will get it. The magnitude, for magnitude you have to do here, okay, not here. This is for a direction. Okay, so you need to take the integration of these dB, and then you will get it this expression. So this is the expression of the magnitude of the magnetic field due to the entire wire. Okay, if you have a longer wire, then you can do it like this. Now in terms of the current density J, we know that current density J is defined as what? The magnitude of the current per unit cross-sectional area. Got it? Or you can say J is equal to I by A. Got it? And if you multiply by dl here in both numerator and denominator, then this will give you the elemental current. But here you will give it that volume, cross-sectional area into length of the conductor, that will give you the volume of the what? Elemental conductor. Got it? So if you try to express that idl here with dv divided by dv there, then you can replace it this what? Idl by what? Idl will be equal to, by using this expression, idl will be equal to what? dv times j, right? If you cross multiplied it. Got it? Then what happen? You will get that idl, instead of idl here you will get as what? J dv. Your J, current density, is a vector quantity. Okay, your current is a scalar quantity, but your current density is a vector quantity. So instead of that idl, you can write as J dv. So dv being volume, a scalar quantity, so you can take outside this cross product. So J cross r vector divided by r cube into dv. Mu naught by 4 pi will be there. Got it? So this is the expression for what? Expression for data of the magnetic field, okay, in terms of the current density J. Here you can also find out both the magnitude as well as the direction. Now lastly, in terms of charge and its velocity, you can express it in this way. Why? Because current, we know that it is a rate of flow of charge flowing through the conductor, let it denoted by d during that small time dt. Then this will represent your current. Okay, don't think that there is not dq by dt. Don't think it in that way. The small current that is flowing during the time dt is denoted by q here. So your I can be expressed as q by dt. So q, you can take it that q dl by dt, where dl by dt is nothing but the velocity. Got it? Velocity of the charge flowing through the conductor. So q dv. So instead of idl in this, okay, we can replace it by what? Q dv. If you want to express in terms of vector quantity, then idl, instead of this, you have to take it as q v vector. Okay, you can take q outside, and v vector cross r vector divided by r cube from here. Okay, so this is the expression of that magnetic field due to the elemental conductor, okay, in terms of the charge and its velocity, right? So in this way you can find it out, the expression of the magnetic field due to the elemental conductor in terms of what current density, in terms of charge and its velocity, like this. Okay, now let's see some important points on this Biot-Savart's law. I'm sorry that there is one T missing here. It should be Biot, B-I-O-T. Okay, Biot-Savart's law. These are the name of the two scientists. Okay, so now let's see. Biot-Savart's law is valid for a symmetrical current distribution. Okay, for a symmetrical current distribution. Got it? It is valid only through that symmetrical current distribution. Got it? Next, it is applicable to only small length of the current carrying conductor. That means it is valid only for elemental current carrying conductor, not for a very long one, but it can be elaborated or expanded to fair approximation up for longer length also. Okay, now let's see. It is not easily verified experimentally because elemental current carrying conductor cannot be obtained practically. This law, that means your Biot-Savart's law, is analogous to Coulomb's law in electrostatics. In electrostatics, Coulomb's law means what? A force between the two charges. So it is somewhat similar. It is almost similar to that of Coulomb's law in electrostatics. The direction vector dB is perpendicular to both vector IDL and the position vector R. Got it? So what happened? As I told you in the previous slide also, what happened? The direction of your magnetic field is perpendicular to both vector IDL and the position vector R, right? I told you. Or you can also take it along a line perpendicular to both what? The plane containing what? This both vector IDL and R vector, right? In that way. Now, if theta, what is theta? Theta is the angle between the position vector and the elemental current carrying conductor. The position vector R and IDL, the angle between IDL and R vector, that angle we call it as theta. So if theta is equal to 0 degree or 180 degree, then what? Your point of observation is lying along the axis of the current carrying conductor. In that case, what happened? Being sine theta or sine 180 degree is equal to 0, what happened? Your magnetic field will be also equal to 0. So there is no magnetic field produced, okay, when the point of observation is along the axis of the current carrying conductor, and this is a case for minimum magnetic field produced by that current carrying conductor. Got it? Depending upon the point of observation, I mean. If theta is equal to 90 degree, that means if your position vector and the elemental current carrying conductor, if that two are perpendicular to each other, means theta is equal to 90 degree. In that case, sine 90 degree is equal to 1. So mu naught by 4 pi, okay, into IDL divided by R square will be there, the value, okay, given by this. So if your point of observation lies perpendicular to the axis of the current carrying conductor, then the magnetic field will be given by this, and it is the maximum case. That means magnetic field produced by the elemental conductor is maximum when the point of observation, okay, of whose position vector R is perpendicular to that elemental what? Current carrying conductor, normal to it. Then what happen? It will give you maximum what? Magnitude of the magnetic field. Got it? Now let's see about the Biot-Savart's law. Okay, due to what? A circular, I mean, this is the application of Biot-Savart's law in terms of the circular coil carrying conductor. Instead of that elemental one, we can go to that of the circular coil, okay, just to find out the magnetic field due to a current carrying circular coil. Okay, so let's take it a circular coil of radius A, like this in the figure. So let's take it like this. Got it? Now consider a circular coil of radius a with center O, okay, carrying current I, lying its plane perpendicular to the plane of the paper. If you take it that this is the plane of the paper, and if you have to take it that this plane of this circular coil is perpendicular to the plane of the paper, let P be the point of observation where we want to find the magnetic field due to this circular coil carrying current at a distance what x from the center of this circular coil. Okay, and consider two diagrammatically opposite edges. Now let's consider two elemental current carrying conductor of length dl at these diagrammatically opposite, okay, points. Got it? And these diagrammatically opposite points makes an angle theta with this x-axis or the axis of the coil. That means angle CPO, okay, is equal to phi. Let's take it in that way, phi. And similarly, as it is along the axis, what happen, angle between this angle CPO, or you can say OPC also, will be equal to angle OPD, and that will be also equal to phi. Got it? So here we are having a right triangle. Got it? Here we are having a right triangle. OCP is a right triangle. And if you want to find the position vector as we have done in the Biot-Savart law, this is the elemental current carrying conductor, okay, elemental current carrying conductor, and this is a point of observation. So this CP is nothing but this will act as just like your position vector. In that case we denote it by R, right? So your CP is a position vector, and let's denote it by R vector. No doubt it can be denoted by R vector. And mind you, the angle between this position vector R vector and the current element there IDL, that angle will be perpendicular to each other. Got it? If you bend this somewhere here, this I mean P happens to be somewhere here, then you may take it that this P and this plane, if you take it that there is a plane perpendicular to this what plane, got it, of the paper, then what happen, every line onto it, whether it is what a straight line like this or bending like this, it will be perpendicular to that vertical plane. Got it? It will be always perpendicular, because this line and that will be what angle between these two will be always 90 degree. So let me draw it that one 90 degree, okay, so that you will not confuse anymore in the subsequent parts. So this angle between what and what IDL and this R vector, this will be perpendicular. This angle will be always what, 90 degree. Got it? Let me mark it here. Okay. Yes, let's go to the description part quickly, and if you want to note down, then you can note down by pausing this video. Okay. So as I said, consider a coil of radius A with center O carrying current I. Okay, this I, current carrying I, lying its plane. Lying its plane means lying of the plane of the coil perpendicular to the plane of the paper here. That means half of this is coming outward, and that half, this dotted line, is behind this plane. Okay, behind this plane, and the half, this CIOD, this is outward, coming outward. Okay, in that way you can take it, right? And the point of observation P is at a distance x from the center of the circular coil O here. Okay, now let's consider two diagrammatically opposite elemental conductor IDL. Okay, here current flows like this, outward, current flows inward. So IDL, that is the elemental length, okay, of two diagrammatically opposite onto the circle. And then I told you that this angle that is made by the position vector with this axis, that is, let's take it that this is phi. Got it? Then what happened, if you take it this as a right triangle, triangle OCP, we know that hypotenuse square is equal to sum of the square of the remaining two sides. So your r square will be equal to what? A square plus x square, right? This is a, this is x. Got it? So what happened? Your hypotenuse, okay, CP will be equal to what? You can mark it as r. CP or PC or PD, okay, these are same because these are congruent triangles here. Okay, congruent triangle, what and what? OCP and ODP are congruent triangle. Okay, so naturally your PC or PD, they are same. Okay, so of equal length I should say. So your PC equal to PD, let's mark it with r. Okay, that will be equal to root over of what? A square plus x square, by using your Pythagoras theorem, right? So like that. So according to that of your Biot-Savart law, then what happened? The magnetic field at this point P due to this elemental current carrying conductor IDL at C will be given by what? Mu naught by 4 pi epsilon naught, as we assume there is a vacuum here, nothing, no material or medium is there, so except vacuum. So what happened? Mu naught by 4 pi epsilon naught IDL sine 90 degree by r square. I told you that the angle between the plane perpendicular to this plane of your notebook and any point, whether it may be somewhere here, the angle between that elemental conductor, okay, the direction of the elemental current carrying conductor and this position vector r will be always 90 degree. If it is somewhere here, also 90 degree. If it is somewhere here, also 90 degree. Got it? So what happened? This theta will be equal to 90 degree in our case of Biot-Savart law. So sine 90 degree is 1, so no need of putting. So your r square, instead of r square, you put it as a square plus x square. If you cross multiply it, then squaring it, then it will be what? R square is equal to a square plus x square, like this. Got it? So in that way, similar to this, if you take it the elemental conductor onto this diagrammatically opposite side D, then what happened? Such similar magnitude will be coming up, but the direction will be different. For this magnetic field dB, okay, that dB will be by applying your right hand rule, or you can apply your cross product of two vector IL and the r vector. Then the direction of the magnetic field for this dB, okay, due to this elemental current carrying conductor at the point C, the direction of the magnetic field will be pointing along this PE. Got it? This PE must be perpendicular to the plane containing this r vector and this IDL here. We have to take it a small direction here, like this. Got it? Not the whole circular one. Got it? The direction of this DVL IDL, that means it will be on that vertical plane perpendicular to this plane. So that small direction, okay, you need to take it that as a line. So that line and this plane, this line r vector, so this PE vector will be perpendicular to both what? The vector IDL as well as r vector. So as here you can see directly that your P vector is perpendicular here. That means your this perpendicular 90 degree, the angle between r vector and your dB vector will be perpendicular to each other. Why? Because your magnetic field will be along the direction perpendicular to both r vector as well as IDL vector. Got it? So it will be directing along this PE vector. Got it? And similarly for this dB vector, IDL vector at this diagrammatically opposite side D, dB prime, okay, if you make it that as dB prime, I will come in the next slide, but let me explain you here in this diagram. Okay, so what happened? Your D, let's take it that the magnetic field at this point due to this elemental current carrying conductor, let it be denoted by dB prime. Okay, so dB prime will be equal to mu naught by 4 pi, same expression will come. magnitude will remain same because it is at the same distance. Got it? I told you that PC is equal to PD, right? And it is equal to root over of a square plus x square, right? So what happened? This magnitude of dB and dB prime will be of same magnitude, but the direction will be opposite, and the direction will be different. Your dB vector is pointing toward PE, and your dV vector will be pointing along this what PF. Okay, your dB prime will be acting along PF. Why? Because this dB prime will be directing along the direction perpendicular to your R vector as well as IDL. Got it? So it will be along this direction. Now when you resolve this dV vector and dB prime vector into two rectangular components, one along the vertical, one along the horizontal, then you will get it these as phi. Got it? So the component near this phi will be the cosine of phi, and the one which is not having this phi will be what? dB sine phi, like that. Here also, if you try to express this dB prime into two rectangular components, then what happen? This will be what? dB prime cosine of phi, and this one will be dB sine phi. So these two, dB cos phi and dB prime cos phi, as dB and dB prime of same magnitude, so they will cancel each other, they will neutralize each other, and only the what horizontal component along the axis will be there. So this will hold good, or this will be true for any two diametrically opposite sides. If you take it for that too also, these two vertical components will cancel each other because they are opposite to each other of same magnitude, so they will cancel, and only that horizontal component along the axis of the circular coil will exist there. So if you want to find out the magnetic field due to this whole circular coil, then we need to integrate such dB sine phi along its axis, starting from somewhere here to that whole circumference. Got it? So let's see in the next slide, okay, how it could be done in that way by taking integration. Now let's see, but I will try to explain you about this dB prime for this one. It will be coming in the next slide. So let me little bit explain about you that one, and then we will switch on to that of those what calculation part. Okay, so let's see here. So dV, as I said, dV is directed along the plane containing dl and r vector. This I have already told you. Now if you take that elemental current IDL at diagrammatically opposite side D, then the magnitude will also remain same, but the direction will be different. Okay, that in the case of dB, it was along the what your DPE direction, but here your dB vector will be directing along this PF vector. So they are not equal, they are different in a different direction. Okay, so if you resolve it, this dV vector into two rectangular component, as I said, you will get it one horizontal component for this dV, one horizontal component, one vertical component here. I mean the horizontal component here, another vertical component here. Got it? So in that way, what happened, we can find it out that, got it? Let me come to that again. Okay, like this. So what happened if you try to do this resolution of this splitting of this dV vector, then you will get the vertical component and horizontal component like this. So these two vertical component will cancel each other, and only that horizontal component exists. Okay, oh, had I not given that one? I have not given the hyperlink. Okay, sorry. Let's quickly go to that one. Yes, we were here, right? So now your dV and dV prime, the magnitude of this dV vector and magnitude of dV prime vector are same, and it will be equal to this. Now as I said, on resolving this, the vertical component will cancel each other, only the horizontal component will exist. And if you want to find out the total magnetic field due to the whole circular coil of what current carrying conductor of radius A, then what happened, you need to integrate this dB sine phi. So your dv sine phi was there along its axis. Got it? So you need to integrate it, as I have said already to you. Now when we try to integrate it, this we need to put the expression of dv as well as sine phi. Sine phi in that right triangle, okay. Sine phi is equal to what? A by that hypotenuse. A is what? It was like this. It was a circular coil like this, and this is your A, right? This is your X, this is your point P, and this is your X, right? And this was like this was marked as C, right? So your phi was somewhere here, right? Phi, got it? Phi is somewhere here. So what happened? Sine of phi means what? Perpendicular by its hypotenuse. Perpendicular is what? Opposite. Okay, opposite to this. Phi is what? Nothing but this is the radius A, and hypotenuse PC is equal to R. So R is what? Root over of A square plus X square. So if you put this expression of dV as well as sine phi, then you will get in this form, right? And you need to integrate, as these are all constants. Got it? Mu naught I, A, 4 pi, these are all constants. So you take it outside the integration, and you need to integrate only this dl. So if you sum up all those small elemental length over the whole circumference, then you will get it the circumference of the circular coil. Circumference of the circular coil is what? Nothing but twice pi A, the radius. Okay, so this is the total length of the circumference of that circular coil. So if you put it all those things, then you will get the expression like this. If there are n turns in the coil, then we need to multiply it by n. If there is only one turn, you will get like this. If there are two turns, then you will get twice of this. So if there are n turns, then you will get n times of this. Got it? Yes, in that way. Okay, and let's try to see the different forms of this expression. Okay, the special case. Now when you take it, this point of observation P, okay, lies at the center of the coil. That means at the center of the coil O. Then what happened? Your position vector, the distance of the position vector P from O, which was denoted by x, will be equal to 0. Got it? If you put x is equal to 0 in that expression, then what happened? It will be coming as mu naught by 4 pi, as like this, twice pi n I, x equal to 0, so it will be A. Okay, that A square and another A from here, if you cancel it, then it will get A only. Got it? Now when P lies far away from the center of the circular coil, that is x is very much greater than A, you can take it. So in that expression of A square plus x square, A being small, you can neglect it. So it will be equal to x square. Instead of A square plus x square, it will be just as x square. So this square and square root will cancel, and in the denominator, I mean x cube will be there, right? X cube. So this A square, pi A square, is the area of that circular coil. Okay, so instead of that pi A square, you can represent it by capital A, where A is the nothing but the area of that circular coil. And we know that the magnitude of this IA, okay, it will give you the magnetic moment of a circular coil. And if there are n turns, then NIA will give you the total magnetic dipole moment of that circular coil. Got it? And magnetic dipole moment we denote it by capital M. Got it? So your magnetic field overall, when the point of observation is very far away from the center of the circular coil, then we can express magnetic field as mu naught by 4 pi twice M by x cube, like this, where M is nothing but this is the magnetic dipole moment, I should say total magnetic dipole moment of the whole turns of the circular coil, which is equal to NIA. IA, the product of the magnitude of the current and each cross-sectional area, will give you the dipole moment for a single coil. If there are n turns, then you need to multiply by n to this so as to get the total magnetic dipole moment. Got it? And it is a vector quantity and its direction can be known from this simple diagram. Okay, if the current is flowing like this in a clockwise direction, and if you are observing from above, then this will have direction just like your south pole. Okay, this represents south. This direction is what? Direction of the current onto that circular coil is clockwise, and if you are observing from the top, this side is facing to the observer. Okay, and that side of the coil will represent what? Just like a south pole. South pole means what? Magnetic line of force will be pointing toward it. Got it? So your magnetic dipole moment will be getting inside. Got it? And if that side of the coil, the direction of the current is anti-clockwise like this, then it will just act just like a north pole. North pole means what? Your magnetic field lines will start emitting from it. Got it? From it. So your dipole moment will be also in the direction of that what? Direction of the magnetic field. That means it will be what? Outward. The direction of the magnetic dipole moment will be inward in this case. In this case, it will be what? Outward, like that. Got it? With that, we have come to the end of this today's class. Thank you.